Welcome back, Calculus. So here I'm going to give you the chain rule again, and some examples and some extensions. So let's start off with let f and g be functions. So for all x in the domain of g, so that g prime of x exists and f prime of g of x exists, the derivative of our composition function h of x equals f composed g of x, which is another way of saying f of x, f of g of x. The derivative of that function, h prime of x, is going to be defined to be f prime of g of x times g prime of x. There's another way to write this using something called Leibniz notation, which I'm going to make a video about pretty soon. But if you already know it, that's okay. I'll talk about it when we get to that video on Leibniz notation. So I'm going to go through a few examples here to show you how this works. These are examples and checkpoints from your textbook. And then I'm going to go and extend this composition rule. So we composed 2 functions. What if we composed 3 or more functions, or 4 or more functions, or so on and so forth? So first, I'm going to make the video jump around. Second, I'm going to do some examples. So here's our first example. This is checkpoint 3.34 in your textbook. So let's suppose we have h of x equal to 2x cubed plus 2x minus 1 to the 4th power. Now, theoretically, I could just expand this polynomial, but that would be huge and a big pain. So what I'm going to do instead is try to find an f of x and a g of x that make this into a function composition and apply the chain rule. So f of x is my outside function, and I think that's going to be x to the 4th. And g of x is my inside function. It's going to be this good old polynomial here. And so if I take the derivative, h prime of x, that should give me the derivative of my outside function with g of x as an argument times g prime of x. So this is going to give me, if I'm taking the derivative of this function here, that would be 4x to the 3rd. But instead of this x, I'm going to use g of x as the argument of my function. So that's going to give me 4x. Oh, I said the x. No, that's going to give me 4 times the g of x raised to the 3rd power. And then I'm going to multiply into that g prime of x. So this is my g of x function. And if I take the derivative, I'm going to stick it right in here. And we're going to get 6x squared plus 2. So this is going to be 4 times 2x cubed plus 2x minus 1 all to the 3rd power times 6x squared plus 2. And it's actually fine with me if you leave that as your final answer. I don't see any real good way to simplify it any further, other than multiplying it all the way out into some huge polynomial. That just seems like a headache. I don't see a direct benefit from that at this point. Maybe there might be a certain application in which you'd want to do that, but I don't see that for here. And so that would be your derivative. What if I have a trig function in the mix though? So we're going to do another example here. And let's say I have this time h of x is equal to the sine cubed of x. So here my outside function, f of x, is x cubed, and my inside function, g of x, is the sine of x. Let me show you why. This one's a little complicated, and I think it might benefit us. So if I take f of g of x like this, that means that I'm saying take this g of x and cube it. And so what is that g of x? That's the sine of x. And then what does that become? That becomes sine cubed of x. So hopefully you buy it. So let's take that derivative then. Then we get h prime of x equals the derivative of the outside function times the derivative of the inside function, like that. And so that's going to be, our outside function was 3x cubed, or was x cubed. The outside function was x cubed. So this is going to give us 3 times g prime of x and the derivative of sine is cosine. So that's going to give us this. We're going to end up with 3 sine x in here times cosine x. And then we can simplify this. We'll end up with 3 sine squared x cosine x. And that will be the derivative there. I'm going to do one example of sorry guys, this quarantine's getting to me. I hope it's not getting to you. I'm going to do composition of 3 or more functions now, and then I'm going to do composition for 4 functions, and then I'm going to try to tell you how I remember this when I'm doing the chain rule. So we can know what we're doing when we take the derivative of a composition of one function, of 2 functions. So chain rule with 3 functions. So suppose I have this function, k of x, and that is, and now I'm going to have 3 functions. So I'm going to make my outermost function green. And then in here, so I have 3 functions. So the first thing I'm going to do is treat this with the original chain rule. And what I mean by that is that I know that if I'm finding k prime of x, I'm going to want to take the derivative of some outside function, blah, blah. I'm going to use the chain rule here. But what I'm going to treat as my outside function is this h. And I'm going to treat all of this function, I'm going to treat this all as my inside function. So I'll take the derivative of my outside function, h prime here, and then leave my inside function, this stuff that I highlighted in red, just drop it right in there. That's what I'm treating as my inside function. And then I have to multiply that by the derivative of all this stuff highlighted in red. So I have to take all of this here, highlighted in red, the f of g of x, all of this, and I have to take the derivative of that. Okay, so I'm almost done, believe it or not. So this is good to go. I just need to take the derivative of this piece. And what happens is I'm going to end up just applying the chain rule again. Let's give myself a little bit more room. So now I have k prime of x equals h prime I'm just copying this from the line above. And then I have to take the derivative of this piece here, which means I'm just using the chain rule again. So let's go ahead and do that. Then I'm going to end up with f prime of g of x, the derivative of my outside function f, times the derivative of g prime of x. So here's what I notice when I have something like this. I'm going to write this all out in one color and then show you kind of how I think of it. So here was my original function, k of x, and this equaled h of f of g of x. Do. Wow, that's a lot, right? And when I take the derivative of this function, this k of x, it's like I'm peeling an onion. So I take this outer layer, my h function, and I take the derivative of that and leave the rest of my onion inside, f of g of x. Then I've peeled off my h layer, and I go into this layer here, f, and I take the derivative of that layer, f of g of x. And then I peel off that f layer, and what's left, g of x, and take the derivative of that, g prime of x. So this term comes out, and I take the derivative of that. This term comes out, and I take the derivative of that. So let's say I had like a huge, horrible mess. Let's say I had, I don't even know if I can fix this, if I can fit this all here. But let's say I had an m of x that was equal to a k of h of f of g of x. Oh man, a lot, right? Don't fear. So first, I take the derivative of that piece. So m prime of x would be equal to k prime of everything inside. H of f of g of x. Let's move my parenthesis a little closer so I have maybe enough room to write this all on one line. Then I take myself and I go right in one more layer and I look at that h. So So now I multiply all of that times h prime of f of g of x. Let's stick with my color palette here. H prime of f of g of x. And now I've handled that layer, and I go in and I handle the f layer, and I multiply this by f prime of g of x. And I've dealt with the f layer, I've peeled that off, and my final layer is the g layer, and I take g prime of x. So when you're doing the chain rule, so this is my pro tip. Derivatives are like onions. They have layers. My niece is obsessed with Shrek the Musical right now. That's probably where this is coming from. They have layers. So start peeling your function. And take the derivative as you go. So I'm going to do one example for you of the composite of three functions. And I'll let you know that in this course, that's probably the highest number of functions that you'll have composed together. I just show you the extension of the chain rule so that when you see it in future courses, you'll be ready and you'll be so good at it. And they will say, "Who taught you Calculus 1?" And you'll say, "It was Sarah." And then I get that credit. So here's our example. Let's say I have k of x equals cosine to the fourth power of 7x squared plus 1. So let's go ahead and do this, and we're going to peel this function. So k prime of x equals my first layer is raising something to the fourth power. So that's what I'm going to do first. So this is 4 times cosine of 7x squared plus 1 to the third power. Now I have to go into my second layer, which is the cosine layer. So then I have this derivative multiplied by negative sine of 7x squared plus 1. And now I go into this layer, the polynomial layer. I have this multiplied by x. And now all I have to do is actually multiply this stuff out and collect my like terms. Not so bad. So this is all multiplication. And the only thing I see really here is that I should combine my constants. So then this derivative, k prime of x, is equal to 56, negative 56, the negative coming from this side, negative 56x times the sine of 7x squared plus 1 times cosine cubed of 7x squared plus 1. And that's it. Not too shabby. All right, so those are the examples that I wanted you to see. I'm not going to prove the chain rule. If I had time in class, if I had you guys in class, I would do it. But I'm not going to do it right now, just because I'm going to give you guys a little break. I'm going to give you a little break and not prove it. If you're curious about it, read through the informal proof they give in the book, and you're